So here's a problem. If we start with a rectangular grid, with two spaces marked as the starting and the ending points, when is it possible to find a path between them, visiting all the spaces in the grid exactly once, and moving only vertically or horizontally at each step? The solution to this problem utilizes a basic mathematical concept taught in the earliest school years, and yet most people's first instinct on it is incomplete. Today, let's take a closer look at what's going on with this problem. My name is Sturdos. I'm on a mission to collect interesting math problems for school-aged children, and I'd like to take you along. If we keep the dimensions of the grid as well as the starting point unchanged, to see what happens if we move the ending point, we can quickly spot a pattern. These are all the endpoints that do produce a path through all the spaces, and these are all the endpoints that don't. If we color the grid like a checkerboard, only the ending points with the same color as the starting point would give us a valid path. Let's pick a different starting point to check. Again, only the ending points with the same color give us a valid path. Let's try a slightly different rectangle with the same starting point as our first cases. This time we get the opposite results. These are the ending points that give us a valid path, and these don't. So what changed here? You might have guessed it. Our total number of spaces in the grid went from an odd number to an even number. If we imagine counting spaces as we walk along our path, we start on the odd number 1, and every step we alternate between an odd number and an even number. If the total number of spaces is odd, say 15, then the last number we get to when we reach the ending point should be 15, i.e. an odd number, just like the starting point 1. If the total number of spaces is even, we count up to an even number, i.e. the opposite of the starting point 1. At the same time, if we imagine coloring all the spaces in the grid in a checkerboard pattern, because we're only moving vertically or horizontally at each step along the path, the color of the next space we land on must be different from the previous one. In other words, as we alternate between odd and even numbers along the path, we're also alternating between the two colors of the checkerboard pattern. This matchup makes it so that all the odd number spaces must be on one color of the checkerboard, and all the even numbers must be on the opposite. Have we solved it then? If the grid has an odd number of spaces, the starting and ending points have to be the same color in the checkerboard pattern. If the grid has an even number of spaces, they have to be different. Let's go back to the first grid and try this with a different starting point. This time, none of the ending points work. Why? If you're enjoying this problem, I made it into a book, so you can share it without giving away the solutions. Check out the link in the description below, and back to the video. Okay, calm down and examine the cases. There are a total of 15 spaces in the grid. If we were to color it in a checkerboard pattern, 8 of them would be one color, and 7 of them would be the other. If we walk along a path through all the spaces in the grid, counting from 1 to 15, we would count through 8 odd numbers. Now imagine starting on the color of the checkerboard that only has 7 spaces. What happens when we count to 14? We have no spaces left of the color we're using for the odd numbers. The 15th step has nowhere to go. So now we have a new rule to add to our list. If the grid has an odd number of total spaces, not only do the starting and ending points have to be on the same color, they also have to be on the majority color on the checkerboard pattern. By the same reasoning, if we take a grid that has an even number of total spaces and black out any space that's the same color as our starting point, we'd be putting the starting point on the minority color, and no valid path through the entire grid can be made from it. The same thing happens if we black out enough spaces for either color to disrupt the balance of the odd and even numbers when counting from 1. Phew, math makes sense again. Now I wonder what other rules we need to add if we move away from rectangular grids. For example, why can we not find a valid path through this irregular grid even though it has the same number of spaces in each color when we put it into the checkerboard pattern? Let me know what you think in the comments below, and until next time, stay curious.